Hey guys, hope everybody's doing okay. What we're going to do today is take a look at something called a reaction quotient. So this is very similar to a equilibrium constant, except we're not always sure if we're actually at equilibrium or not. So if we're given a set of values, a set of concentrations, how do we know if a reaction is actually at equilibrium? So a couple ways to figure that out. One way is to find something called a reaction quotient, which is what this lesson is going to primarily focus on. Okay, let's look at another way first, and then I'll go through how to find reaction quotient, what it means, and we'll go from there. It's a relatively short lesson today, but really important one as well, tying together a lot of the stuff we've done in equilibrium so far. So before we get into that too much, it's really important to review the meaning of K, our equilibrium constant itself. So let's take a look at just a couple of different scenarios here on the screen. KC, KEQ, KSP, whatever. We've learned we have a lot of different K whatever values right now, but they're all basically equilibrium constants. Just with the little subscript there might mean you have gases if it's Kp, a solubility product if it's KSP. Still an equilibrium constant though. If K is equal to 1, what does that mean? So if we go back to our first lesson, our first main lesson on this stuff, if K is equal to 1, then the concentration of products is equal to the concentration of the reactants, right? That means the reactant and product concentrations are exactly the same. This is pretty rare, right? So it's a misconception that students think that reactant and product concentration are always the same at equilibrium, and that is false. All right, they're very rarely the same. Remember, once we reach equilibrium, we have an equal rate of transfer, an equal rate of forward and reverse reaction, not equal concentration of reactant and product. So if K is less than 1 or greater than 1, what does that mean? So if you remember, our K whatever expression is your concentration of products over concentration of reactants. So if you just do some simple math, if K is less than 1, that means your products have to be smaller than your reactants, right? It means you have a bigger denominator here if K is less than 1. So if that's true, then the concentration of products is less than concentration of reactants. And if K is greater than 1, it means your products, your denominator is larger than your your numerator up here is larger than your denominator. Okay, your products are greater than your reactants. So concentration of products greater than concentration of reactants if K is greater than 1. Okay, important, really important to remember this. It's something we talked about a lot when I introduced this. So how do we know if a reaction is at equilibrium or not? One thing you can do is measure the concentration now, and then measure the concentration again at a later point in time, and again at a later point in time, and keep doing that. If the reaction's at equilibrium, something should be true every time you measure your concentration. What should be true is that the concentration won't change. Okay? So remember, we talked about it on the previous slide and a couple lessons ago. When you're at equilibrium, it is equal rate of forward and reverse reaction, so the concentration of reactant product remains consistent. So the concentration won't change. If you look at this, we're starting with some initial conditions, right, of N2, H2, and NH3. Okay, the reaction proceeds, so clearly the H2 and N2 are decreasing in concentration, while the NH3 looks like it's increasing in concentration. Then after a certain point in time, about right here, the concentrations don't change anymore. So if I collect data right here, I would have a certain certain concentrations of N2, H2, and NH3. If I collect data again, a few seconds later, my concentrations have changed, right? The H2 has decreased, the N2 has decreased, and the NH3 has increased. If I do it again, they've changed again, so not at equilibrium yet. So I get to this point right here. Okay, I have my values there for my concentrations. I take it again right here. They didn't change. I take it again right here. They didn't change. So once I hit this point right here, equilibrium has been established. All right? So I have a couple lines on the screen here that show you that. You need at least 2 data sets where the concentration does not change. All right, so very similar to what I had drawn on here. It's one way to do it. It's a little more longer, and you need some lab equipment and things like that. Another way to do it is to find something called a reaction quotient. So what you can do is, if the current, okay, that's important, if the current concentrations are plugged into the equilibrium expression, and that ratio is equal to KEQ or KSP or whatever, then the reaction's at equilibrium. So you want to take your current conditions. We're not sure if the current conditions are at equilibrium or not, right? So we want to take the current conditions, plug them into your equilibrium expression, see what number you get, and compare it to what the KEQ value actually is, what the equilibrium constant actually is. Depending on how they compare, we can tell if we're at equilibrium or if the reaction needs to progress in the forward or reverse directions. All right? So here's an example. Same one on your note sheet. You have H2 and N2 placed in a container and allowed to react. After a few minutes, concentration of H2, N2, and NH3 are given to you. KEQ for the reaction is 0.105. All right? These conditions here, okay, really, really, really important here. These conditions here, you don't know if we're at equilibrium or not. It doesn't say we are. All right, so we can't just assume that. These are some condition at some point in the reaction. All right, so if I could get rid of some of this. All right, so if I'm given these conditions, right, I don't know if those conditions are here or here, which is when I'm not at equilibrium, or are they here or here when I am at equilibrium, all right? So I need to know, are those conditions something over here when I'm not at equilibrium, or is something over here when I am at equilibrium? So here's what we do. Set up a equilibrium, a reaction quotient, all right? A reaction quotient setup, all right? Looks like this. You want to plug in your current values into the equilibrium expression to determine the ratio. So when you do this, like, notice how K is always products over reactants, right? Your KC, KEQ, KSP, whatever. Concentration of products over concentration of reactants. Q is the same thing, all right? The only thing here is Q stands for reaction quotient, all right? We don't know if this ratio of product to reactant is at equilibrium or not. So we need to figure out what it is. All right, so this is super easy stuff because you know how to write the K value, right? The K expression, I should say. So the Q expression is the same thing, except we have Q there instead of K. The ratio at any given point in time is this. Right? So we don't know if we're at equilibrium or not. We don't know where we are on that previous graph I showed you. If Q is equal to KEQ, then the reaction's at equilibrium, right? If your current conditions are the same as your equilibrium conditions, then of course you're at equilibrium. But if Q is less than K or greater than K, then we don't really know, then we know what way the reaction has to progress to reach equilibrium, and we know we're not there. All right, so let's figure it out. You have this problem. These values, again, they're given to you here. We don't know if we're at equilibrium or not. So we set up our Q expression. Okay, if we don't know if we're at equilibrium, and the best way to tell is look at the problem. Is the reaction at equilibrium? So clearly we don't know here, right? Set up a Q expression. Q is equal to NH3 squared. Okay, it's our product over reactants. N2 to the first times H2 cubed, because the coefficient 3 there. Okay, this is the same as our Kc expression, except we don't know if we're at equilibrium, so it's Q. Plug your numbers in. Okay, take a second, copy that down, and figure out what Q is. If you actually calculate it out, you'll get Q is equal to 0.80. That is not the same as your KEQ value. So since Q and KEQ are not equal, we know we are not yet at equilibrium. Okay, to figure out which way our reaction needs to proceed to reach equilibrium, we have to compare our Q value to our Kc or KEQ value. So again, quick recap here, Kc is 0.105, same as KEQ, and Q is 0.80. So clearly Q is you know, way greater than KC right now. All right, so what does that really mean here? If Q is greater than KC, that means that you know, your ratio here is definitely too big, right? So we need to take this ratio, and remember, the ratio is products over reactants. We need to take this ratio and make it smaller, right? I need to get this 0.80 ratio of products to reactants down, right, to 0.105. Okay, so I need to decrease it by a decent amount here. Well, remember, if you have products over reactants, how can I make this fraction smaller? Well, the only way to make this fraction smaller is if I decrease my numerator, all right, and I increase my denominator, right? That's the only way mathematically to make this number smaller. Okay, so what does that mean then? If I need to make my numerator smaller, that means, you know, my numerator are my products, right? I need to decrease the product that I have, and my denominator, which I want to make bigger, right here, I need to increase my reactants. So what's going to happen here? What way does the reaction need to go to reach equilibrium? If I need to decrease the concentration of product and increase the concentration of reactant, my reaction needs to proceed to the left. I need to go in the reverse direction here to reach equilibrium. So the way, like, my current ratio is this 0.80, I'm too product heavy, okay? I need to go back to the reactant side, make this ratio smaller so it becomes equal to my Kc value, all right? So to quick summarize that here, if Q is greater than K, which is what we just had, then the products are too high and the reactants are too low. All right, so it's giving me a value larger than KEQ, which again is our constant at equilibrium. So in this case, Q needs to get smaller, that's what we just talked about in the last example, to reach equilibrium. So again, reactants on the left, products on the right. How do we make Q smaller? Well, we have to decrease the number of products and increase the amount of reactants. So too much product, reaction should proceed to the left in order to reach equilibrium. All right. If I proceed to the left, my products will decrease and my reactants will increase, and that will help my ratio become equal to KEQ. All right. Really important to know that. But honestly, if you just think about it a little bit and you know how to math a little bit, then you could say, all right, my current ratio is too big. How do I make my ratio smaller? It all goes back to knowing this foundational knowledge that your equilibrium expression and your Q expression is products over reactants. What can I do mathematically to change that and to modify that? All right, so reverse reaction will proceed and progress at a faster rate to reach equilibrium. If I have the opposite, then the opposite is true. So if Q is less than K, then again, Q expression is products over reactants. It's less than KEQ. So this ratio right here is too small. Okay, so I'm not at equilibrium here. What does Q need to do then? Well, Q needs to get larger because I just said it's less. Okay, it's less than K. How do I make it larger then? Okay, reactants yields products. That's my general setup here. Too much reactant in this case. Okay, my Q value is too small, so the reactants are larger than the products. That's how I get a value less than KEQ here. All right, so the reaction needs to proceed to the right. Okay, so I need to, in order to make Q bigger, my products needs to increase, my reactants need to decrease. If I want to decrease my reactants, increase my products, I will shift to the forward direction. Okay, forward reaction proceeds at a faster rate to reach equilibrium. This will happen, so we will shift forward until this Q value gets a little bit bigger, a little bit bigger, a little bit bigger, until it reaches KEQ and we're at equilibrium. All right? So a couple practice problems, then we'll wrap this up. So consider this reaction. These are in your packet, so we could flip to those and give them a try here. Write the equilibrium constant expression for reaction. Okay, so take a second and do that. We're just writing the equilibrium constant expression. So that is our KEQ expression here. All right. So to do that, we have KEQ equals, and it's concentration of products. So we have SO3 squared over reactants. So we have SO2 squared times O2. Right, that's it. So that's our KEQ expression. We wrote these a million times so far. Letter B, write the reaction quotient expression. So if we are at any point in time and we're not sure if it's at equilibrium, okay, so we said any set of conditions here, let's write the reaction quotient expression. It's actually the same exact thing. The only difference is it's Q. Okay, so KEQ is at equilibrium, right? Equilibrium constant expression. Q is at any point in time during your chemical reaction in general. Okay, so Q is equal to products over reactants. So same thing. SO3 squared over the concentration of SO2 squared times concentration of O2. All right. Now look at letter C. It says a reaction vessel contains 0.150 molar sulfur dioxide, 0.150 molar oxygen, and 2 molar sulfur trioxide. Predict the direction of the reaction in order to reach equilibrium and to show a calculation. So we have the general setup here. All right. So let's plug in our values then. So I don't know if these values down here are, I don't know if they're at equilibrium or not because it doesn't tell me. So I plug them in for my Q expression, right? It's a minor detail, but really, really important. If you don't know if you're at equilibrium, this must say Q here. If you put KEQ, it's wrong because you don't know if you're at equilibrium or not. So let's plug everything in. We have 2 molar sulfur trioxide, so we'll have 2.000 molar squared over SO2 was 0.150 squared, and O2 is also 0.150. Okay, plug it in your calculator and you will get a Q value of 1,185. Okay, predict the direction the reaction must shift to reach equilibrium. So let's see, we have our Q value of 1185, KEQ is 3,900, so Q is less than KEQ in this situation, right? Way less. What does that mean? If Q is less than KEQ, we need to take this ratio here and make it bigger. So I need to increase my products, I need to decrease my reactants in order to make this ratio Q larger. All right, so if I want to increase my product and decrease my reactant, then the reaction needs to shift in the forward direction and go left to right to create more product and to decrease concentration of reactants. Okay, these are really easy. Once you get the hang of it, Q is less than KEQ, we shift forward. If Q is greater than KEQ, we shift to the left. Simple as that. All right, the next one. Another chemical reaction. I give you the KEQ value. The reaction vessel contains half a molar of hydrogen, 0.500 molar iodine, and 0.750 molar hydrogen iodide. Again, predict the direction we'll shift to reach equilibrium. Show calculation. So I read a problem like this. It says to predict the direction the reaction must shift to reach equilibrium, so I'm not sure if I'm there. So it's Q equals, not KC or KEQ, right? It's Q equals product, H2, times I2, over concentration of reactants, HI squared. Okay, because the coefficient of 2 here. All right, plug my numbers in. For H2, it was 0.500 molar. I2, that should be a bracket. I2 was 0.500 molar. And my reactant, HI, was 0.750 molar squared. Okay, what do we end up with? We plug it into our calculator and we get a Q value of 0.444. All right, let's compare it. So in this case, Q is 0.444. That is greater than 0.2 5. All right, so Q is greater than KEQ. All right, so what should happen here? In this situation, since Q is greater than KEQ, this ratio right here is currently too big. I need to make it smaller. So I should decrease my product, increase my reactant. The only way for that to happen is if my reaction goes from right to left. All right, so it's going to shift in the reverse direction to reach equilibrium, right to left. Okay, last one here. Okay, you guys can give this one a try, and then we can check our work on it once you wrap it up. So for this one, write the reaction quotient expression. So it says specifically reaction quotient, so that is Q. Okay, so it's products, so CdCl4 -2. And there's no coefficient there, so you know no exponent. It's aqueous, that gets included in our equilibrium constant expression, or reaction quotient expression in this case. Divided by your reactants, so it's cadmium 2 times the chloride ion to the 4th, because we have a coefficient of 4 here. All right. So for part B, reaction vessel contains 0.100 molar cadmium ion, 0.500 molar chloride, and 0.250 molar tetrachlorocadmate ion. That's fun to say. Again, predict the direction of what's going to happen here. Okay, let's plug stuff in. We have 0.250 molar of that weird ion. Cadmium was 0.100 molar. And the chloride was 0.500 molar. We have to go to the 4th power. All right, take a second, plug it into your calculator, and see what we get. All right, so in this case, if you plug it in, you should get a Q value of 40. All right, so KEQ is 108. So we have Q is less than KEQ. All right, 40 is definitely less than 108. So what does that mean? It means, again, for the 3rd time in a row here, going through the setup this way, this is what you guys should do if you're trying to figure these out. If Q is less than KEQ, this ratio is too small. How do I make this ratio bigger? Well, I have to increase my numerator, so I have to increase the product, and I have to decrease my reactant. So again, here's our equation. Reactants yields products. If I need to increase my product, okay, and decrease my reactant, the reaction should shift in the forward direction, left to right. So the reaction will proceed in the forward direction, okay? Equilibrium will go to the right in order to, or the reaction will go to the right in order to establish equilibrium. Okay? That takes care of it. So this really takes care of the first half, maybe a little more than half of our current unit. So we started with equilibrium vapor pressure. We moved into writing Kc or KEQ expressions. We learned a little bit about Kp with gases, KSP, solubility product, and now Q, which will tell us, for any reaction at any point in time, are we at equilibrium or not? So it could be with pressures, it could be with, with KSP. So all the other, equilibrium constant lessons apply here. And just remember that the reaction quotient is to determine if we are at equilibrium or not. So once you find Q, you'll compare it to your KEQ or KSP or KP, and then take it from there. See if it's equal to that value. Is it greater than or less than your equilibrium constant? And then see how equilibrium will have to proceed, how your reaction will have to proceed to reach equilibrium. Okay? We'll work on some practice problems. If you have any questions, let me know. That's really about it. All right, thanks guys.